All right. Today we are going to be looking at solving polynomial equations. You guys have done this before, but we've only done them with quadratics. And in this chapter, what we've been doing is obviously working with much larger polynomials, x cubes, x to the fourths. We even saw some that were, x to the seventh. And so our goal is to be able to solve those. When we solve them, what we are looking for is what we call the zeros of a function. Okay. Or the, it helps if you can spell zero. The zeros of a function, also called the roots of the function, and the solutions. Okay. And those are where they cross or touch the x-axis. So over here, you can see we have another zero. Okay. They're called zeros because at that point, that's where the y value, the function, actually equals 0. So we could say y equals 0 right here, or we could say f of x equals 0. It means the same thing. Okay, and we can actually see the x value where that happens. So for example, this one here on the left, the x value where it crosses the x-axis is right here at 0. So 0 is a 0, we say. And it also touches the x-axis right here. So the y value comes down and y gets to 0. What's the x value? That's the answer we're looking for. 1, 2, 3. So when x is 3, the y value is 0. So our answer would be 3. This actually has what we call multiplicity of 2 because it hits it on the way down, and then we consider it a touch again on the way up. But we'll see more of that and how that looks in an equation as we go forward. Now, as I said, we have learned how to solve quadratics. Remember, quadratics are x squared equations. And so let's just take a look at those methods that we used. So these are methods for solving quadratics, quadratic functions. We practiced these last semester. It's our first topic, basically, after we did some review. First method we learned was the square root method. You have an x squared equals a number. We could square root both sides. And remember, we always got plus or minus when we square rooted both sides. So 8 squared is 64, and negative 8 squared is also 64. So it had two solutions. And all of our x squared quadratic equations, they had two solutions. After the square root method, we learned the complete the square method. This not the preferred way to solve quadratics at all, but it was useful for graphing quadratics. We could find the axis of symmetry with it. We could even write the equations in vertex form by completing the square. And if you recall a little bit, we had to get the constant to the other side. Then we had to find a number, b over 2. So we took the b value 4, divided it by 2, and squared it. And then we could add it to both sides. The left side would be a perfect square at that point, and then we could use the square root method. Again, not a preferred method to do it. If we could solve everything with the square root method, we'd love to. However, this only worked when there was no b term, so it has limited uses. Then we went into solving by factoring. Okay. And we've been practicing factoring a ton in section 4.4, so we're going to use this idea of factoring to help us find the zeros. Okay, the complete the square problem and this factoring problem are identical to each other, and you notice we get the same answer regardless of how we solve the problem. Special note also here, though, is once we had it factored, we used what was called the zero product property, and we'll discuss that in a little bit as we start to solve these big polynomials. And then lastly, our most powerful method was using the quadratic formula, and that was x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And that was very powerful because that could be used all the time. And sometimes we couldn't solve problems by factoring because they're prime, but we could always then solve them with the quadratic formula. And we even got, if you remember, some imaginary numbers as our solutions. So that kind of sums up our methods for solving quadratics. As we go forward now, we're going to apply some of these methods to these bigger polynomials. One of the methods we could use to solve any of our quadratics would be to graph it. Okay, and this is the graph I had on that first page. And you can see, we could just graph it and say, hey, where does it touch the x-axis at? We'd say, well, when x equals 0, it crosses the x-axis, and when x equals 3, it crosses. And we got our solutions, okay? And the advantage is, yeah, that's really fast. In fact, on Desmos, if you just touch your finger or stylus to a 0, it actually will pop up with the solution, and it would say 3, 0 at that point. And that means we know that x equals 3 is a solution. The problem with just relying on the graphing method is you got to have some sort of technology, either a graphing calculator, which most of you probably don't know how to use yet, or software, and we've been using Desmos while we've been at home. Okay, and it does work pretty darn well, but even with that technology, it's not always accurate. For example, if 1/3 was a 0, Desmos would actually give you a 0.33, I think. And 1/3 is not equal to 0.33. Okay? It's actually equal to 0.3 repeating, but Desmos would not show that. And so you'd get close to the answer, but it wouldn't be the perfect answer or the exact answer, which is what we are looking for. So how can we do this? If we can't always rely on graphing because we don't have the tech, or because we have these answers that are going to turn out inaccurate, what can we do? To solve these higher order degree polynomials, the method we are going to use is basically factoring and the zero product property. Okay, we will also use some of these other methods we've learned, like synthetic division, to help us use factoring and the zero product property. Now, the zero product property basically says if you have two things multiplied together and they multiply to 0, then one of those, A has to equal 0 or B has to equal 0. That's the only way that you can multiply two numbers and get a 0. And it's not only two numbers, it can be two expressions. So if I had like x minus 4 times x minus 3 equals 0, then one of these factors, either the x minus 4 or the x minus 3, had to equal 0. And once we've made that decision or gotten it into this form, then we can actually solve these equations, these little linear equations. So let's use this method on that function up there. Now that is the graph of that function showing off to the left. And to factor this guy, the first thing we want to do, actually before we factor it, is we want our function equal to 0. Okay, in this case, we are basically asking the question, hey, what x value makes the, think of f of x as y, equal to 0? Because that's where it crosses the x-axis. That's where we find our quote-unquote zeros. So we just go through our factoring methods. Oops, that's an 18x there. Make sure we got everything. We'll do our GCF first. It looks like we can take out a 2x, giving us x squared minus 6x plus 9 equals 0. Okay, then we're going to factor that polynomial. The a value is just 1. Okay, so we can run over here and go, all right, we can just use c as 9. Let's find our r times s. It could be 1 times 9 or 3 times 3. But they have to add up to -6. 9 and 1 add up to 10. 3 and 3 add up to 6. Now, I want a -6, my b value there. So we're just going to see what happens if they're both negative. Okay, and they still satisfy both conditions. Negative 3 times negative 3 is still a positive 9, but now they add up to negative 6, and so I know my factorization. 2x will be x minus 3 and x minus 3 equals 0. And now we can actually use the zero product property. We've got three factors here. This is factor 1, 2x. Factor 2 is the x minus 3. And factor 3 is also x minus 3. And to solve these, we just take each factor and set it equal to 0. Okay, 2x equals 0. Divide by 2, and we get x equals 0. Next one, x minus 3, we set u equal to 0. Add 3 to both sides. X equals 3. And then the blue one there, x minus 3 equals 0. We add 3. X equals 3. And those are our three solutions to this polynomial. And we can see them right here. There's x equals 0 causes y to equal 0. X equals 3 causes y to equal 3. That was causes y to equal 0. That was on the way down. It touched it. And then as it turned around, it hits it again, we say. And so x equals 3 again, y equals 0. Okay, so it has three solutions. And we just say x equals, for our final answer, 0, 3, and 3. But when you get repeats like this, in this case we got repeats of 3, this is called multiplicity. We actually dealt with this before. And in this case, since it happened 2 times, multiplicity of 2. Which means 3 was a double 0 or a double root or a double solution. Okay. So we factor it. We set each factor equal to 0 and then solve those for x. Let's look at our example here. In this case, we're asked to find the zeros, just like we did. Okay. And then we are going to make a little graph of it. All right. So let's set this function equal to 0. Oops. Negative 2x to the 4th plus 16x squared minus 32 equals 0. And let's factor out our GCF. I'm going to go ahead and take a negative 2 out of this. Give me x to the 4th minus 8x squared plus 16. Now in this case, and I could have done it on the last one, but the last one I also pulled out an x, if you recall. This coefficient, or this factor that you pulled out, it has no x associated with it. And so you can actually divide this left side by that number. In this case, negative 2. You have to do it to the other side as well. But negative 2 over negative 2 is just 1. So really, because there was no x that we factored out, we would have no solution from that factor, and we don't even have to worry about it. So we just got to worry about this x to the 4th equation. Okay, now this is what we call quadratic form. We've actually seen a couple of these in our factoring section. It goes 4, 2, none. Okay, everything's basically doubled. Usually our quadratics go 2, then 1, then 0. But if you double them, you get a 4. 1 times 2 is 2, and 0 times 2 is 0. This is still in quadratic form, we say. And we can factor it just like we did the last one, using that AC method. In this case, our C value is 16. There we go. C equals 16. And they got to add up to negative 8. Now this tells us they're both going to be negatives. And we just list our R times S's. 1 times 16, 2 times 8, or 4 times 4. And when we add these, they've got to add up. Oops, I should put an equal sign there. When I add these, I get 17, I get 10, and I get 8 for this last one. So this last one's what I want. But I got to get a negative 8 in the middle. Okay, so we're going to make them both negative. Negative 4 times negative 4 is still positive 16, but now they add up to the negative 8. It's a little bit tougher now because instead of being x to the first power, because this is an x to the fourth, it becomes x squared minus 4 times x squared minus our other 4 down there. And we'll go ahead and keep factoring these. These are both differences of squares. This is an x squared minus a 2 squared. So we can use our difference of squares, x minus 2, x plus 2, times x minus 2, times x plus 2. And we set each one of these equal to 0, and we solve them. X minus 2 equals 0, so x is 2. X plus 2 equals 0, subtract 2, x equals negative 2. Here's another x minus 2. It's going to give us the same x equals 2 and another x plus 2. So we get 4 solutions for this thing. 2 different zeros, 2 and negative 2, each with a multiplicity of 2 because they both happen 2 times. Let's mark these on our graph now. So here's our solutions. X could equal, and I'm going to write it this way, negative 2, and I'm going to put an MP behind it of 2 and positive 2 multiplicity of 2. And I've also seen this notation because these are what we call zeros. You'll see this often with a DZ, and that stands for double zero. That just means it's a 0 that happened 2 times. And 2, DZ. We could have triple zeros, okay, which would mean negative 2 was the solution 3 times. Just so you're aware of some of the different language that you'll hear. Let's go ahead and graph these solutions. Now remember, these are x-intercepts where the y value is 0, so you'd make your coordinate axis like I have here. There's our x's and y's, and 2 is a solution, so we'll just make 2 marks. That's our 2, and negative 2 is a solution. Now, because these are multiplicities, we know that this graph is just going to come down, touch that point, and then turn away. Or maybe it approaches it from the bottom and touches it and turns away. But we do know it's going to turn away from those points. It's going to do the same thing on the left, either do this or it's going to touch it and do that. So let's see what else we know about this function. One of the things that is always easy to find is the y-intercept, because the y-intercept is where the function crosses the y-axis. And to find the y-intercept, all you have to do is let x equal 0. Find the f of 0. And this is very simple because when we substitute in 0 for all our x's, anything times 0 is 0. And so when x is 0, this function goes through negative 32. Now I'm clearly not going to mark down here to negative 32. So I'm going to put one down here, and I'll just label it negative 32, and that's another point that it goes through. So now I know it has to go through that. Let's see, what else do I know about this function? Ooh, I know it's even. So I know the ends have to go in the same direction, because that's its highest degree, or the degree of the polynomial, and it's even. So it's either doing this on the right and this on the left, or it's doing this on the right and this on the left. My lead coefficient is negative, and that means it's going to do that right there. So the only way this graph could actually fit in here now, because the left-hand side has to go down, it's going to touch it right there. So the left-hand side has to go down. It has to turn around here. It hits the y-intercept. It must come up like this, touch it, and turn back around. So it kind of looks like an M when we get done. And yes, that is a lot of math that we just did. Okay? I'll try and give myself a little more space on this next one. Actually, the graph. These are just some examples of solving again. Okay? Solve this equation. It should have a 0 behind it, but it doesn't. So I'm going to set it equal to 0. They should either be set to 0, but they should equal something. If they're not equal to 0, we're going to get it equal to 0. And this should be an x to the first. I know that. Just because if it's supposed to be just a standard quadratic equation. Okay, so let's check. Let's see if we can factor this thing. Okay, we look for a GCF. We take out a 4. X squared minus 10x plus 9 equals 0. This 4 has no x associated with it, so if we divide both sides by 4, we just get x squared minus 10x plus 9 equals 0. We're going to just factor this. C equals 9. We're looking for a negative 10 in the middle when we add these, so it could be 1 and 9 or 3 and 3. If I add 1 and 9, I get a 10. If I add 3 and 3, I get a 6. So we don't want this one. Now we needed a negative 10, so we need both these to be negative. Now they add up to negative 10, and they still multiply to 9. And so we can factor it. X minus 1 times x minus 9 equals 0. We set the first factor equal to 0 and solve it. Add 1 to both sides. We set the second factor equal to 0. We add 9 to both sides. And we get x equals 9. Solutions, x equals 1 and 9. And we're done. Okay, so not super hard. Okay, if you've done your factoring, you'll be in great shape for this. Here's one that's a little unusual. Okay, notice how this equation, it does not equal 0. It says equals 14x minus 3. In order for us to use that zero product property, it has got to equal 0. So it must equal 0 on the right-hand side. So before we do any work, we're going to subtract it from the right, because that'll make it 0 over there. And we got to subtract it from the left. Now I'm sitting it right in the middle here, because when I write down my polynomial, I want that thing in standard form. Plus 24x. And now I'm ready to start factoring it. Looks like I can take out a 2x, giving me x to the 4th minus 7x squared plus 12. Now, you could, I want to be complete my explanation here. If you wanted to get rid of this 2, you could at this point. You could divide both sides by 2, and it would 2 over 2 is just 1. It's not going to really matter or save you much time if you do that. Let's go ahead and continue factoring. Now I know this thing's going to factor as a binomial. See how it's 4, then 2, then 0. There's no x. It's just next to the 0 power there. This is in quadratic form, so we can factor it like normal. Okay? In this case, our c value is 12. Our r and s must give us a 12 when we multiply, but they have to add up to a negative 7. So it could be 1 and 12, but that's not going to work. That gives us a 13. Let's see here. Could be 2 times 6. Yeah, but that adds up to an 8. Could be 3 times 4. There's the one we want. That adds up to a 7. But again, note we want a negative 7, so we'll make everybody negative like that. Negative 3 times negative 4 is still positive 12, but now they add up to negative 7. And so it's x squared minus 3, and it's x squared minus 4. Now, we didn't do this on the last one, okay, because we could factor them very easily. And in fact, we could factor this x squared minus 4. We've already done that in a previous problem, x minus 2, x plus 2. But now I'm going to show you another option you have. Here's our first factor, here's our second factor, and here's our third factor. Note, it's all multiplication here. It equals 0, and therefore the zero product property says either 2x equals 0, or x squared minus 3 equals 0, or x squared minus 4 equals 0. The green one over here we divide by 2. X is 0, there's one of our answers. The blue one here is quadratic still. It's an x squared. We can't factor it. Okay, 3 is not a perfect square. But if you remember the method 1 for solving quadratics, because that's what we have now, one of our methods was the square root method. We take the 3 to the other side, square root both sides, x equals plus or minus the square root of 3. That's two answers, positive square root 3 and negative square root 3. This quadratic, just like all quadratics, gave us two solutions. And again, this x squared minus 4, I could do difference of squares, but heck, I might as well use the square root method on him. He has no b term. And I square root both sides, plus or minus 2. So we ended up with 1, 2, 3, 2, and negative 2, 4, and 5 solutions for this fifth degree polynomial. So our solutions we'd write are 0, and we can just write plus minus root 3, and we can write plus or minus 2. And we are done. Last example. Going back to like our second example I showed you at the beginning, where not only do we have to find these zeros of the function, but we're going to draw a little sketch of it. Again, we just write it down in standard form, and we ask ourselves, what makes u equal 0? And we start to factor it. GCF. That quadratic. Quadratics, hopefully you guys are starting to see when they got three terms like this. It factors into two binomials. And the first terms here always multiply to give you this first term. So in this case, x and x. For your 6 now, you could have a 1 times 6. This is like doing your R and S, or a 2 times 3. Note our b value is 1 right there. Okay, and notice our c here is actually a negative 6. So that negative 6 tells us either the 1 is negative or the 6. They can't both be negative because then they'd multiply to a positive. Because that negative 6, one's negative, one's positive. We just don't know which one. This b value helps you out though. It says when I add them, I want a positive 1. That means I want my 3 to be positive and my 2 to be negative, because when those two add together, they do give me a positive 1. So it's negative 2 and positive 3. Here we go. Set my x equal to 0, the first factor. Set my x minus 2 equal to 0, and set my x plus 3 equal to 0. X equals 2 when we add 2 to both sides. X equals negative 3. Let's graph this guy. So we'll put a point at x is 0. We'll put a point when x is 2. And we'll put a point when x is negative 3. Those are the places where it either touches or crosses. In this case, it's going to be crossing because it doesn't have any multiplicities. You only get multiplicities when it touches it and turns away. Let's see what we know up here in our original function. Degree is odd. Remember, when your degree is odd, it's two choices. In this case, it doesn't make those smiley and sad faces. It either does this or it does this. Okay? This one looks like it's going to have a hump in the middle too. Let's look at our lead coefficient here. Our lead coefficient is positive. That means the right-hand side is going up. But because it's an odd degree, that darn left-hand side wants to go down. So, right side goes up like this. Then it must come down somewhere around here and go back up. But then after it goes back up, it must come back down. Now, I don't know how high it goes up to at this point. I don't know how low it goes down. I might try to calculate, some of these things. I could say, okay, what if x is 1? And you could actually find the f of 1. It'd be 1 cubed plus 1 squared minus 6. That's just 2 minus 6. It goes down to negative 4, it looks like. So 1, 2, 3, 4. If I wanted to be more accurate, I certainly could make some effort to be more accurate. But for today's stuff, you don't need to do that. I just want to show you that you could. So it actually does something like this, a little bit deeper. And then you might find a point right in the middle here, negative 1.5, and see how high it goes. But I would certainly be just fine with that first graph we had. If I can get back to him, there he is. Like this. Okay, you're in pretty good shape at that point. All right, that's all I have on this stuff. I know it was a lot, everybody, but we are starting to put it all together now.